Hello. As part of our software engineering project, we studied the concepts of static analysis tools and their internal workings, the rules they use for finding bug patterns, their pros and cons, and their usefulness in the software industry, etc. We analyzed two very popular static analysis tools, FindBugs and PMD. Also, we ran these tools on two open source projects, Eclipse and iTrust, for a better understanding. We have discussed the internal workings of these two tools in our blog post and podcast provided in the references at the end. So Abhay, before we show our viewers the working and a detailed analysis of these tools, can you briefly talk about static analysis in general and about these two tools?
Yeah, sure. Static analysis is basically analysis of software that is performed without actually executing the programs. And a static code analysis tool automatically checks the source code for compliance with a predefined set of rules or best practices set by an organization. Static analysis tools are fast and efficient in finding code defects, especially in larger code bases, including older legacy codes or newly created codes as well. A static code analysis tools can help you with your code review process by detecting areas in the code that need to be refactored and simplified, finding areas of code that may need more testing or deeper review, identifying potential software quality issues before the code moves to production. Now coming to the two tools that we have analyzed, the first tool is FindBugs, which is a defect detection tool for Java that uses static analysis to look for more than 200 bug patterns, such as null pointer dereferences, infinite recursive loops, bad uses of Java libraries, and deluxe. FindBugs can identify hundreds of serious defects in large applications, typically about one defect per 1,000 to 2,000 lines of non-commented source statements. FindBugs is an open source that has been downloaded more than 200,000 times and is used by many major companies and financial institutions. It can be used from the command line or with Ant, Eclipse, Maven, NetBeans, and Emacs. The second tool that we worked was PMD. PMD is an open source rule-based static code review analyzer that analyzes Java source code based on the evaluative rules that have been enabled during given program execution. The tool comes with a default set of rules which can be used to unearth common development mistakes such as having empty try catch blocks, variables that have never been used, objects that are unnecessary, or something like that. PMD also allows users to execute custom analysis by allowing them to develop new evaluative rules in a convenient manner. The tool comes with a relatively easy to use command line interface and at the same time can also be integrated with popular development environments such as Eclipse.
Now we will demonstrate the installation, working and report analysis of these tools. First of all, if you want to install either FindBugs or PMD on your machine, you can go into the help option of Eclipse, choose install new software. You will be prompted for entering the URL. You can enter the URL for FindBugs or PMD, whatever you want. You can check this and carry on with the installation process. We already have the tool installed on our system, so we'll skip this step. We have tested FindBugs and PMD on iTrust and Eclipse. For this demonstration, we will be just focusing on iTrust. We'll be running PMD and FindBugs on it. So first of all, when we run, if you want to run FindBugs on iTrust, just right click on iTrust. We have this following option of FindBugs here. It provides us with a list of options such as FindBugs, clear bug markers, save to XML if you want to save the report as XML or something like that. We click FindBugs here, and then it asks me if you want to run the process in background or something like that. It carries on its execution, checking the source code against various rules that it has developed, that it has already in its database. FindBugs, after running its various tests, lists the various bugs that it has found. You can see it here. On clicking the various options, we can see exactly on which line, in which file the bug is present. Also, if we right click a particular bug, we can have an option to get its info. Here, find bugs gives us the confidence level, the rank of the bug, also which category the bug is related to. The violations that PMD finds are actually divided into 3 categories: correctness, bad practice, and dodgy. The category here is correctness. Correctness violations are those that represent an apparent coding mistake, resulting in code that was probably not what the developer intended, like wrong type handling or instance of checks that are always true or false respectively. Similarly, bad practice violations are something like violations of recommended and essential coding practices. Examples of it includes hash code and equals problem. The third violation is dodgy, which represents code which is written in a confusing way and is therefore less transparent and robust. Now if we move back to the bug explorer, we can see the various errors that are listed. Just select one of them. It says that there is no check performed for a null argument. Just double click this error here, and it will show us exactly on what file the error is happening. Here, as you can see, there is no check performed for the object O if it's a null value or not. It's just comparing the values of the object. So as we can see here, the explanation provided by the static analysis tool find bug is quite intuitive in itself, and the developer can easily make out what the error is about. So now we will be running the source code iTrust on PMD. If you go to the home directory of iTrust and right click it, you can see the option of PMD, and it gives you various options if you want to check the code, clear previous violations, etc., etc., if you want to generate the reports or something like that. So we click the check code option here. Now it has started its processing, and it will check the source code against all the 313 rules that it has already got in its database. So when the run of PMD is complete, it gives you a violations overview window where all the packages that contains error are listed here. If you select individual packets, you will see exactly where in the files, exactly what files have errors. Also, it gives you 5 flags having different categories: red indicating blocker violation, cyan indicating critical violation, green indicating urgent violations, pink indicating important violations, and blue indicating warnings. So it's quite intuitive in itself. If you just want to have the blocker violations listed, you can deselect all the other options here, and it will just list you the blocker violations. Double click the source code file here, and it will tell you what exactly the error is. So it will tell you here that there's something wrong with the variable naming conventions. So if you click this here, it shows you where exactly in the source code it's happening. So here the variable name starts with the uppercase letter, which obviously is wrong, so it will show you a variable naming conventions violation. Similarly, there are errors in the other files also. So most of the errors are variable naming conventions, method naming conventions, variable naming conventions, and along those lines. Also, one point to note here is that these are based on the criticality of the bugs. So red indicates the most severe one, and blue indicates the least severe one.
So following is a summary of the error reports generated by PMD and find bugs on Eclipse source code. You can see the numbers and types of violations in this slide. PMD generated 19 critical violations, 446 urgent violations, and 26 important violations, while Findbugs generated 40 correctness violations, 105 bad practices, and 67 dodgy violations. Similarly, following are the violations generated on the iTrust source code. Both PMD and Findbugs found different kinds of errors on the source code. Most of the errors found by PMD were of type Boolean instantiation, duplicate imports, unused imports, and unnecessary constructor, while most of the violations generated by Findbugs were of type abstract factory cannot be resolved to a type, non-transient non-serializable instance field, and non-transient non-serializable instance field in serializable class. This slide shows the comparison between the two tools and their strengths and weaknesses. Some of the strengths of Findbugs are that it has low false detection rates and is fast because it uses bytecode for analysis. PMD's strengths are that it finds bad practices and real defects. PMD's weaknesses are that it does slow duplicate code detection, while Findbugs' weaknesses are that it is not aware of the sources and needs compiled code.
With this, we come to the end of our screencast. Some of the observations that we made during the course of this project were that the purpose of static analysis is not to replace the traditional testing, but to augment it. Static analysis will allow the organization to deliver better quality code to the QA, and it will be reflected in a more effective and efficient QA testing. It also differs from traditional testing methods as it can identify bugs or issues that may not be apparent to a tester, but can have negative impacts on the product stability, performance, security, or maintainability. A QA tester will test the functionality and performance of an application under expected operating conditions, while static analysis will look at the code from a technical perspective and identify issues that might be missed based on the parameters used to structure the QA test program. Also, we know from our experience that regardless of how experienced and talented a programmer may be, he/she is likely to make mistakes while writing programs. Unfortunately, while for smaller programs these mistakes are usually few and often have limited impact only, as programs grow, even small mistakes start having unexpectedly severe impacts. Consider a small program that creates a few unnecessary objects or variables that are never used in the program. In the realm of this smaller code base, the performance impact of these objects or variables will be negligible. However, in much larger code base, these unnecessary objects will be large and many in number and can thus greatly impact the system's performance. Therefore, identifying and eliminating them beforehand is vital. This is where static analysis tools comes into picture, as they can statically analyze both large and small code bases and can be used to detect such critical issues well in advance. Okay, this concludes our presentation on static code analysis. Hope you enjoyed watching. Thank you.